Welcome to the second video lecture on compressible fluid flow. In this video lecture, we will discuss the topic compressibility of fluid. Consider a fluid of mass m and of volume v initially subjected to an equal pressure from all directions. When we increase this pressure by an incremental value, say P plus dP, it results in compression of the fluid. Because of this, the volume of the fluid is reduced, but the mass will remain same. Hence, after the increase in pressure, we get mass is equal to m unchanged and volume reduced by V minus dV. Pressure is nothing but compressive stress from the mechanics point of view. And we know that when the compressive stress is applied from all directions, it will result in volumetric strain. So, using this, we can define the bulk modulus of elasticity of the fluid. It is compressive stress over volumetric strain. Here, the compressive stress is due to change in pressure, and volumetric strain is change in volume over the original volume. This results in the following equation, that is K is equal to minus V dP by dV. We know that the density is mass divided by volume, and using this we can replace the volume terms and obtain the equation as shown. That is K is equal to rho into dP by d rho. From the equation, we see that the bulk modulus of elasticity of the fluid can be used to account for the change in volume or density of the fluid due to change in pressure. Hence, the bulk modulus of elasticity is taken as a measure of compressibility of fluid. In order to define bulk modulus of elasticity, we can set the denominator value, that is the volumetric strain, equal to 1. Then we see that the bulk modulus of elasticity is equal to change in pressure. From this, we can define bulk modulus of elasticity as the pressure that has to be applied to a fluid in order to change the volume or density of the fluid by 1%. This value shows that how difficult it is to compress a fluid. From this, we can define the compressibility of fluid. We see that the bulk modulus of elasticity shows how difficult it is to compress a fluid. Hence, the inverse of this gives the compressibility of fluid, that is the ease with which a fluid can be compressed. Hence, the term compressibility is defined as inverse of bulk modulus of elasticity. When it comes to the gases, we see that the combustion can be done in two ways. It can be done isothermally or isentropically. If it is done isothermally, then bulk modulus of elasticity is equal to the pressure applied on the fluid. If it is done isentropically, then bulk modulus of elasticity is the product of pressure applied and specific heat ratio. Let us take some examples to understand the compressibility of fluid in a much better manner. Here I have taken the bulk modulus value for water and air for comparison. For water it is 210 atmosphere and for air it is 1 atmosphere at standard conditions. This means that in order to reduce the volume of water by 1%, we have to apply a pressure which is 210 times greater than the atmospheric pressure. Whereas for air, it is just 1 atmospheric pressure to bring about the same effect. Hence, water is considered as highly incompressible, whereas air is considered as highly compressible in nature. In general, we can infer that liquids are incompressible in nature and gases are compressible in nature. But this doesn't apply straight away for a flow process. In order to understand how the compressibility affects the fluid flow process, we need to understand some more different topics which we will be dealing in the following slides as well as in the following lectures. In order to understand the compressibility effect of a fluid flow, we have to understand what is a pressure wave, how it is generated, and how it influences a fluid medium. If there is any disturbance in a fluid medium, it will release a certain amount of energy which is absorbed by the fluid molecules surrounding it. This results in the fluid molecules to vibrate at a higher energy level. During this vibration, the molecules comes closer to each other. During this time, it will interact with its other nearby molecules and transfer this energy to those molecules. Because of this, the initial molecules will lose energy and move further away from each other, whereas the molecules that receive this energy will start vibrating at a higher level and will start coming much more closer to each other. Then this energy is transferred to its nearby molecules and so on. Hence, we see that this energy results in compression and expansion of fluid molecules within the medium. Thus, any disturbance in a fluid flow results in the release of energy, and this energy propagates through the fluid medium in the form of a pressure wave. And as the pressure wave passes through the medium, it will result in change in thermodynamic state of the fluid. It can alter the pressure, temperature, velocity and density of the fluid through which it passes. As a wave progresses, there will be a region which will be influenced by the wave, and there will be also a region which is unaffected by the wave. If we take all the molecules that are currently affected by the wave at a particular instant and we take the locus of all those molecules, we get what is known as a wavefront. The wavefront separates the affected region from the unaffected region. Sound wave and velocity of sound wave. A sound wave is an infinitesimal pressure wave that is transmitted through the medium. These waves are of very feeble energy and results in extremely small changes in thermodynamic properties of the fluid. In most cases, the disturbance caused by any point sources within the fluid medium are of infinitesimal in nature. The pressure waves resulting from the disturbances, when received by the human ears, are interpreted as sound. Hence, the study of sound waves will help us to understand the pressure waves produced by a point source. Now, in order to understand how it is related to the compressibility of fluid, let us take a look at the table given in the slide. The table has certain substances, its density value is given, and the velocity of sound of through each substance is also given. We see that as the density increases, the velocity of sound increases. This is because as the density increases, the fluid particles are much more closer to each other. Hence, the transmission of energy from one molecule to another and thereby the transmission of sound wave takes place at a faster rate, and because of which we will have a higher velocity of sound at higher value of density. From the topics discussed so far, we can come to the following conclusions. The density increase results in decrease in compressibility of fluid. When there is an increase in density, the velocity of sound through the fluid also increases. If we combine both these conclusions, we will get the following inference. That is, as the compressibility effect increases, velocity of sound decreases. So within a flow, if there is any change in the density, that will be reflected in the velocity of sound. Hence, velocity of sound can be used to determine whether a flow is compressible or incompressible in nature.